let us learn to design a FIFO, first in, first out. So let's say we have module 1 and module 2, right? So if module 1 wants to send data to module 2, so then it can use a FIFO. So FIFO is like a queue. So whatever goes in first comes out first. Say M1 is your first hardware block and it runs with the clock, say clock 1. Let's say the clock frequency is 50 megahertz. And M2 runs with clock 2 in the same chip, and this runs with say 100 megahertz. So how do you synchronize data between M1 and M2? So that is where FIFO comes into play, and FIFO helps us in synchronizing data naturally. Even when you have two very independent clocks, say this is at 17 megahertz and this is at say 33 megahertz, you can still transfer data from M1 to M2 without any drop in data and at the maximum possible speed. So when we have two clocks interacting with the FIFO, now clock 1 can write into the FIFO at its own speed, and clock 2 can read from the FIFO at its own speed. Now both need not read and write at the same time, and clock 1 is independent and it can write into the FIFO whenever it has data, and clock 2 can read from FIFO whenever it is free to read. Right. Even though if it is a queue, we usually have a circular buffer so that you can just continue the queue without any break. So let me show you that. So this is your buffer and it's folded, right? So let me draw the address spaces. Right. So if this is the beginning of your buffer and this is address 0, 1, 2, 3, 4 and so on, and then you come all the way to the last few addresses. Let's say you have a 64 byte memory, and so this is going to be 62 and 63. So this memory strip is kind of folded. It's folded back and made into a kind of a circular buffer, right? Okay. So this circular buffer will have two pointers. So one is usually called the head pointer, another one called the tail pointer. So when the FIFO is empty, it will point to the same address and it will point to the 0 address. So this is your FIFO. It is 64 byte FIFO, and so let's say the status of the FIFO is currently empty, right? Because your head and tail are equal, right? Okay. So head pointer is the pointer that will help us write into the FIFO. And so wherever the head pointer is pointing to, so that is where we will write. Tail pointer will show us from where to read. The FIFO will have a data in. So let's call it say buffer in, and a data out. So let's call that buffer out, right? And a clock 1, this is going to govern the write. So you have a write enable, and a clock out So this is for reading out, and read enable for reading out. Right. So if module 1 wants to write something into the FIFO, then it will issue clock 1 and write enable, and then also supply the buffer in. So when it gives the clock, and the head pointer is showing us where the FIFO should load the incoming data, and the data will load into the 0 address, and the head pointer will move to 1. So head pointer is pointing to the new location where data has to be returned next. And empty is no longer 1, it is now 0 because it's not empty. There is 1 byte of data in the FIFO, and your tail is not equal to head anymore, right? And to keep track of the number of bytes in the FIFO, we will have a counter. So a counter will keep track of the number of bytes in the FIFO, and so currently there are 1 byte. There is only 1 byte in the FIFO. Let us say your M1 chooses to write again into the FIFO. So now it will write into the address 1. So address 1 will be filled, and the head pointer will move to 2. And now your counter will increment to a value 2. So there are 2 bytes. Your FIFO has 2 bytes of useful data. Let's say your M1 writes 2 more bytes. So if it writes 2 more bytes, then your address 2 will be filled, and also address 3 will be filled. So your head will now point to address 4. And so your count would have updated to a value 4. So there are 4 bytes in the FIFO. Now let us say your M2 starts reading data. So since your MT is not 1, so that means there is some data in your FIFO, and your M2 can read data from FIFO now. So when the clock 2 is given and read enable is given, FIFO will start pushing out data into buffer out from the tail pointer. So the tail pointer is currently pointing to 0, and this data will be sent out to buffer out, and your tail pointer will increment in the same direction as head. Tail pointer will increment and now point to address 1. Since 1 data is read, and now the address 0 does not have any data, and your count reduces to 3. Now MT is still 0, so your M2 can continue to read some more bytes. So it will give the next clock 2, and read enable, and your FIFO will put out the next data on buffer out. The next data will be fetched from address 1. So once address 1 gets cleared, your tail is going to move to address 2. And your count is going to reduce to 2 because you have only 2 bytes left in the FIFO. Let's say your M2 issues 2 more reads and reads 2 more bytes from the FIFO. So your FIFO will push out data from address 2 and address 3, and now your tail pointer has again merged with your head pointer, and now your MT has to turn on again because all the data is finished, and your count reduces to a 0 value, and again your tail is equal to head now. And yes, all the data has gone out from 2 and 3. So your FIFO is empty again, but unlike the initial case, your tail and head are merging at address 4, right? So if your FIFO had some data and then it empties, so your tail and head need not be at 0. It could be anywhere on the circular buffer. It could be at it's at 4 now. It could be at 62, it could be at 47, it could be anywhere. Right. Let's say your M1 starts writing again, and it writes from 4 and all the way up to your address 62, right? So it is written up to 62. So now your head will be pointing to 63. And so your addresses from 4 till 62 is all filled. 63 is still empty. Your head is pointing to 63. So your count should be 64 minus 1, 2, 3, 4, 5. So that is 59. So you have 5 empty locations in your FIFO, and your total location is 64. So your count should be 59. And your empty flag will no longer be 1, and your tail is no longer equal to head. So what if your M1 writes once more? So if it writes once more, so it will fill 63, the location 63, and then your head will shift to the address 0. So you see, that is where the circular buffer helps. So when it reaches the last address, it just hops over to the first address and continues on. So there is no break in the increment of your head pointer. And your count value becomes 60. So let's say your M1 writes 4 more times. So it will fill the address 0, and then 1 and 2 and also 3. So now your head will merge with the tail, right? So it is caught up with the tail, right? So all the locations in the FIFO are full, and your count value has become 64, and empty is still 0, but your new flag has to be on, so that is your full flag. So this full flag indicates that all your FIFO locations are written and there is no more place for M1 to write to. So your FIFO is full, and unless M2 reads some data, your FIFO is going to be full and M1 cannot write further into the FIFO. And your tail is again equal to your head. So this is called the full condition of your FIFO. So your head cannot move further unless your tail moves at least one location. So if your M2 decides to read 1 byte, then your tail will increment and point to location 5, and now it creates an empty space for M1 to write 1 more byte. So in this case, your full is no longer 1 because there is 1 empty space, and your tail is not equal to head anymore, and your count reduces to 63. So this is how your FIFO works, and your FIFO helps in transferring data from one module to another module seamlessly. So M1 can transmit data in its own frequency, and M2 can receive data in its own frequency, and everything is managed well. Let us now look at the code for the FIFO that we just discussed. First, let's keep a single clock and discuss a FIFO based on the single clock. Now there are different versions of FIFO. So single clock FIFOs are the simplest ones. So let's do that first and then upgrade it to 2 different clocks. Right, so you have a common clock, a reset, just to reset the internals, and you have the buffer in and buffer out. So these are data in and data out. The write enable, and this is the control signal to write into your FIFO, and read enable, this is to fetch data from the FIFO. These two are flags, buffer full and buffer empty, and your FIFO counter. So FIFO counter, if you want, you can have it outside, otherwise it can be an internal signal. Right, so you define all the inputs and outputs. So all these are 1-bit inputs, and your buffer in and buffer out are 8-bit input and outputs, and 2 status signals, buffer empty and buffer full, and your FIFO counter. Actually, since we have 64 locations and your FIFO counter has to go 1 higher, so you need 7 bits for a FIFO counter. So I just defined all of them as 8-bit. And these are your reg, internal reg, and you have the memory defined here. So your memory is an 8-bit 64 location memory. Your MSB bit is 63 and your LSB bit is 0. Right, so let's start with the code. So the first always block gives the status flag. So when your counter is 0, that means you have nothing in your FIFO, so your buffer empty goes high. Right, so your buffer empty is high whenever your FIFO counter goes 0. So this always block is entered whenever your FIFO counter value changes. So whenever the FIFO counter is updated, you come and check if you have to set buffer empty or buffer full. So when your FIFO counter has reached 64, that means all the locations in your buffer are full. So then you'll have to set the buffer full flag. So when buffer empty is high, then nobody can read from the FIFO, and when buffer full is high, nobody can write into the FIFO. So these flags are used for internal purposes as well, to check if somebody can write into it or somebody can read from it. The next always block helps you set the FIFO counter. So you enter this always block based on posage clock or on reset. So it's an active high reset. So we come in, we check for reset. So FIFO counter is one thing we want to reset. And if reset is active, we reset the FIFO counter. If reset is not active, then we come in because of clock. And here reset is asynchronous reset. And if asynchronous reset is not active, we've come in because of clock. And when we come in, we check if we have to update our FIFO counter. Now there is one case when there is activity, we don't update the FIFO counter. That is when we are both reading and writing. So since we have the same clock, we might do that in one clock. We might both read as well as write. So when write enable is 1 and when read enable is 1 and you're able to write, that means your buffer is not full, and you're able to read, that means your buffer is not empty. So if both the conditions are satisfied, then you don't have to update your FIFO counter. So FIFO counter value is held as it is, just for this condition. Now if this is not true, then maybe you're writing or reading. So then let's check for writing first. So if you're writing, and you can only write if buffer is not full. So if you're writing and buffer is not full, then your FIFO counter is incremented by 1. And if you're reading and if you are able to read, that means there is buffer empty is not high, then you decrement the FIFO counter. That means you reduce the number of items that are available in the FIFO. And if none of these conditions hold good, then you just hold the FIFO counter as it is. So this manages the FIFO counter. This always block manages FIFO counter. Now the next always block helps you fetch the data from the FIFO. So at the clock edge, so if you are getting a clock or asynchronous reset, you get inside this always block, and if reset is active, then you give 0 as your data out, your buffer out. If reset is not active, then you go inside the FIFO and fetch the data. So that happens when your read is active and you're able to read, that means your buffer is not empty. Then you've used the read pointer. This is the tail, right? So the tail pointer, the read pointer here, we've just renamed it as read pointer. Use the read pointer, get into the buffer memory and fetch the data and put it at buffer out. Now if this is not true, that means if either read enable is not 1 and if buffer empty is true, then you don't do anything to the buffer out, you just hold the buffer out as it is. So this always block is for fetching data from the FIFO. The next always block is for writing data into the FIFO. So like the earlier case, we again come in because of posage clock. Now here there is no activity of reset. So at the clock edge we come in. If write enable is 1, if it is 1, then we also check for buffer full. If buffer full is not true, then we can write into the buffer. So we take the data in and use the write pointer. So this is the head pointer, and head pointer gives us the address, and we use this address, go to this memory location and put the data in. Else, so we just hold the data. So your synthesis tool is wise enough to understand this. Just keep the data as it is. So this posage clock does the data writing for you into the FIFO. Now we have to manage the pointers. So to manage the pointers, we come inside at the posage of clock or at reset. So at reset, we initialize our pointers. So pointers are by default initialized to 0. And if reset is not active, then we work on the pointer. So if you are writing into the memory and we are able to write, then we have to increment the write pointer, that is the head pointer. Else we keep the pointer as it is, the write pointer as it is. Now if you see, this section and this section are both concurrent. So this is for managing your write pointer, that is your head, and this is for managing your tail pointer, that is your read pointer here. So both are concurrent, both happen simultaneously within this else block, right? Okay, so yeah, so while your write pointer is being updated, you also check for read signal. If your read enable is active and you're able to read, that means your buffer is not empty, then you increment your read pointer also. So your read pointer also moves in the same direction. Tail also moves in the same direction, but tail goes after head. Tail cannot overtake head at any point, right? So else just retain your read pointer as it is. And so that is it. And this is the code for a simple single clock first in first out hardware block.